A 128 pound weight is attached to a spring having a spring constant of 64 pounds per foot. I've already calculated M here. Now this is the spring constant K. The weight is started in motion with no initial velocity by displacing it 6 inches above the equilibrium position and by applying a weight to the weight and external force. Now to find the differential equation, we just have m x double prime, there's no damping since there is no air resistance, plus k is 64, x is equals to the external force 8 sine 4t. Now I'm going to divide through by 4, so x double prime plus 16x is equals to 2 sine 4t, and I'm going to add in the initial conditions as well. No initial velocity means x prime 0 is 0, and displacing it 6 inches above equilibrium means x of 0 is minus 6 over 12, which is minus half. That's A. For B now we have to solve this differential equation. Now we first try and solve the homogeneous problem by obtaining the auxiliary equation, which is m square plus 16 is 0, so m is equals to plus or minus 4i, and so this is the complementary function is c1 cos 4t plus c2 sine 4t. Now to determine xp, the particular solution, we look at the form of the input function here. So our particular solution will have the form a cos 4t plus b sine 4t, and because there is duplication between these two, so I'm going to multiply by t. Now we find xp prime, which is minus 4a sine 4t plus 4b cos 4t multiplied by t plus a cos 4t plus b sine 4t. This by applying the product rule. So xp double prime is minus 16a cos 4t minus 16b sine 4t multiplied by t plus minus 4a sine 4t plus 4b cos 4t, and differentiate t, we get 1 plus, now we differentiate this part, minus 4a sine 4t plus 4b cos 4t. Now let me simplify this. I'm going to take the minus 16 out, and I get a cos 4t plus b sine 4t multiplied by t minus 8a sine 4t plus 8b cos 4t. Now we plug this into our differential equation. Xp double prime plus 16xp is minus 16 a cos 4t plus b sine 4t multiplied by t minus 8a sine 4t plus 8b cos 4t plus 16 times xp, which is a cos 4t plus b sine 4t multiplied by t. And you can see straight away that we can cancel these two terms off, and so we get just minus 8a sine 4t plus 8b cos 4t, and this is of course equal to the input function, which was 2 sine 4t, and we determine a and b by comparing coefficients. So we have minus 8a equals to 2 which means A is equals to minus 1 over 4, and 8b is 0, so b is equals to 0, and so xp is just minus 1 over 4 t cos 4t, and so our xt function is xc plus xp, which is equals to c1 cos 4t plus c2 sin 4t minus 1 over 4 t cos 4t. Now if you plug in the initial conditions, you will find that c1 is actually minus half and c2 is actually 1 over 16, and this is our final answer. Now you will notice the t here, and this means that as t gets larger and larger, what happens is the displacements will become larger and larger as well. So if you were to draw this graph, you will get a graph that looks something like this. Initially the amplitudes are small, but they will get larger and larger, and this is a case of resonance. When this occurs, we say resonant occurs, and this is not an ideal situation for the system.